We're ready to start. So welcome everyone. This is the first Flatiron Machine Learning Science Summer School. Hopefully we can do it, I don't know, maybe every 2 years or every year, but we're really excited to have you, and we think this can be a really exciting school. There's this, so the backstory to this school is that there's this summer school called the Machine Learning Summer School. It's been a series for like 20 years now, but there's not many events like this where they teach machine learning courses for science. So we thought it would be great if we had a machine learning summer school for science applications. So that's what this event really tries to target. Michael, do you want to share out the lecture series?
Yeah. So I mean, you all know this from emails, I guess, but basically we'll have 2 weeks of lectures, and then followed by a couple of weeks, sort of end of June to sort of beginning of August of projects with mentors. The lectures, we had initially tried to basically tally this into 1 week of basically ML, pure ML intro, and then in the second week we've got sort of ML applied to sciences. Due to a lot of scheduling constraints that might be mixed up a little bit, but that's the sort of general theme. There is also another workshop that'll be going on in the second week, an ML physics workshop with researchers coming in from all over the place. And you will see in the schedule in the second week, there's lots of empty slots in the morning, and you'll probably be able to attend this workshop as well if you're interested, or work on your projects if you already have your projects. I have contacted we have contacted your mentors to try to meet with you this afternoon, so that today we've got basically 2 lectures. There'll be Miles and Rob in the morning, then there'll be lunch, and the mentors that have time will try to meet with their students to sort of like start talking about the projects and stuff. That's basically it.
And then, yeah, I thought we could do, so I'll just list off the names, and I think we'll each introduce ourselves, and maybe we could go around the room, everybody introduce themselves. So the organizers include myself, Michael, Domenico, Sayavash, and Shirley and Natalie, who aren't here yet. And then the admin team, we have Kristen and Shannon on the 17th floor. So in terms of additional notes for computing, so I think so it's kind of difficult to set up access to our main computing clusters, or kind of generally. So I think we'll do this on a project by project basis. But I think for most projects, it's actually better if, I think most people use Google Colab. So we can sponsor like Google Colab Pro, and it's a very easy way to kind of do deep learning on your laptop. In terms of where to work, there's space on the 17th floor of this building to kind of work with your laptop, and then you can also work in your center. So whoever your mentor is, they have a center that they belong to, and there's kind of desk space there, and you can also work on the 11th floor of 162. So there's a lot of space there. Kristen, do you want to share the other
let me go
information?
through just a couple like administrative logistical points for everyone. So I'm Kristen. I think I met most of you via email, so it's great to see everyone's faces. A couple logistical things. First, you'll need to obtain your Simon's Foundation badge this week. It'll look kind of like this. So it won't be a name tag necessarily, it'll be a badge. They're not ready today from what I've heard, but they should be ready by tomorrow. Shannon is our program coordinator for the summer programs. She sits on the 17th floor, and she should have them ready for pass out. So I'll go ahead and make sure everyone does get an email when they're ready, and you'll just have to let her know your name and she'll give you your badge. This is what you use to get into Simon's Foundation or Flatiron Institute. So when you came into Math for America, they had just a printed off list with your name on it. But when we go into Simon's Foundation or Flatiron, you'll use this badge and be able to buzz in. So that will give you access at any point throughout the day without having to check in your name or anything along those lines. You'll also set up your IT account and Seamless account today. I think some of you received a handout from me. There's also additional little handouts right at the check-in desk if you want to grab one from IT. Your personal email should have a message from IT that says your Simon's Foundation IT packet secure sent. You want to open that and read your tech briefing. This afternoon might be a good time since you have some free time. And you can use this to set up your Seamless account. So this is how you're going to order your lunch and dinner each day. So this week, because we have 2 programs kicking off, we have breakfast and lunch available on the 17th floor. You know, I think you're welcome to come up and run some, you get some food. After this week, you'll have to order your food each day. So there's available restaurants and you'll be able to choose what you want and use the funding source from Simon's Foundation. So you want to make sure you get that set up ideally today as well. So there should be instructions in your IT packet, but I'll be around today as well. So you're welcome to ask me or send me an email and I can help you out.
Chris, I have a question. Can they enter the institute in 162 today, this afternoon, even though they do not have the badge yet?
You would have to as a guest. So you would basically just be a visitor. So in this case, you would have to show them the things I sent in the email yesterday, your government ID, proof of vaccination, and your health attestation form. So today it would be a little bit more similar to your entrance here, except they're also going to check, you know, government ID as well. Once you have your badge, they won't check any of those things. You'll be able to just like buzz into the building. Okay, so like I said, Shannon will be here the entire 2-week duration while you're at Math for America. She'll actually be here the entire summer. So if you have any immediate day-to-day questions, you can always run up to her desk on the 17th floor. You might have seen her, she's behind a huge like computer screen right when you walk up there. I also have her email. She can help with any immediate questions. You can also email me with any questions as well. I think many of you have been in contact with me already. And like I said, this week we do have breakfast, coffee, and lunch available on the 17th floor. But week 2 and onward, you're going to want to order from Seamless. And if you are working in your centers or on the 11th floor, you'll already be in the building to get your lunch as well. We have the Wi-Fi information here. There, in terms of the presentations in this room, there's not ceiling mics, but there's like some mics on the table. So if you are trying to be on the Zoom and recorded with your question, if you have a specific question, you can go ahead and use these microphones. In terms of bathrooms, there's men and women's restrooms on this floor. You can see on the side and also the check-in desk, there's the code to get into the restrooms. There's also gender neutral restrooms on the 17th floor that requires no code. So that's basically the gist for Math for America, but if you have any specific questions, please let us know.
Okay, thanks, Kristen.
Yep.
Okay, so yeah, I think now we will do organizer introductions. We'll just introduce ourselves, and then maybe we can go around the room and hear everything. Cool. Okay.
Yes, that's me. Hi, yeah, I'm Michael. I'm a research scientist at CCM since February 2020, and before that, I did a postdoc at UC Berkeley for 3 years, and originally, like, I did my PhD in France. And the topics that I typically work on or have worked on in the past are sort of forward modeling, encoding models of brain activity, and currently I am more working on basically wavelet approaches to doing some form of machine learning in science that can range from sort of the scale of molecules to more recently I've worked on cosmological data with similar approaches, And one other thing that I like to work on is sort of alternatives to backpropagation in neural networks. Sort of like working on with weird architectures and sort of having fun with that. So that's basically it for me.
What is that?
What is what?
That image.
Oh yeah, I mean, there's some fun facts here. I grew up next to a place in Germany with like you can find it without any roads or annotations at Google Maps because there's just a huge hole. And yeah, it's a coal mine. It's wonderful. And then the other thing is that's my brain. It's a bit lopsided. I do know this because I got an MRI scan of myself. That's basically my two pieces of information.
Hello, I'm Siavash. I am your CCN affiliated organizer, so Center for Computational Neuroscience. Anyone here working with CCN mentors? Okay, cool. Nice to meet you. Nice to meet you before. So my interests are, yes, actually I did my PhD in theoretical physics looking at a lot of objects like this Feynman diagrams. But afterwards I pivoted to machine learning and neuroscience about 6 years ago now. I work between machine learning and neuroscience. Basically, what can we learn on each side from the other? Also, because of my background in theoretical physics, I'd like to apply, say, theoretical techniques to all of this. I also really like working with different centers. It's one of the amazing things at the Flatiron Institute is that we have a lot of amazing scientists from different disciplines. So I'm, for example, involved now in a project with Miles, who's at CCA, and we are looking at cancer detection, which is neither CCA nor CCN, it's more like CCP. But there's a lot of like cross-region collaborations going on. So I hope that you guys will be able to like work on the fields here also. So I'm actually at the other building. So we have 3 buildings. There's one here and then 62 and 160. I'm at the third floor of 160. That's where the CCN is, and some of your lectures will be there also.
You have not told us about some facts, so this is nice.
Oh yeah. So I moved around a lot. Like I did 2 years of my undergrad one place, and then 2 years another place, and then a master's and a PhD at all different institutions. So overall, I've been at 7 places. And when I was in Cambridge, I used to have Stephen Hawking walk by my office every day. Yeah, it was fun. One day I heard like him like reading a passage from like Harry Potter, like he was like passing outside. And I was like, wow, he's reading into Harry Potter. I went and saw that he was just a technician trying to tune his chair.
So I'm obviously not Shirley, but she's not here yet, so I'm going to give her introduction. So Shirley works on kind of many different problems in astrophysics and the applications of machine learning to them. Particularly, she's interested in cosmology. She advises many students at NYU, Princeton, and locally at the Flatiron Institute. She's interested outside of science in reading about public policy, geopolitics, and she's also doing a startup for fun. Her fun fact, I don't know this story. She recently organized a bachelor party, got banned from Airbnb. I can't tell you anymore. I don't know about this. So she's at the CCA, the Center for Computational Astrophysics. You can find her on the 5th floor of 162. Okay.
Yeah. I'm Domenico. Sorry, okay, this is more boring than the other organizers. I was the first to do this, and our instruction was let's put some bio info. But then this morning I discovered that all these guys made more fun things, and okay, forget about my bio. Yeah, that's better. And I'll leave that like this. I'm the CCQ. I'm Domenico, and I'm the CCQ organizer of the school. How many of you are from CCQ? Let's say mentored by CCQ guys. Maybe someone from Anima, but they are not here. Well, yeah, I'm assistant professor at the University of Bologna in Italy, but I'm here for 2 years as a visiting scholar at CCQ with a project that is trying to combine all the things that you see here. I'm an expert. Well, I like to do to tackle the electronic properties of materials and try to combine this in the recent year with machine learning approaches, let's say neural network. So if you are curious, just ask me. I can do more. Yeah, I'm at the Flatiron Institute, so 162, 10th floor, that's CCQ part of the building. And that's all from my side.
So my name is Miles Kramer. I work on machine learning for astronomy, particularly I've started to recently work on turbulence a lot, or fluid dynamics. So like, on the ML side, I mainly work on graph ML, so graph neural networks, and especially interpreting them and kind of doing symbolic regression on them. In terms of not science things, I really like graphic design. I like being a coffee snob and insulting coffee places. And I like watching and playing basketball. I'm really bad at it, but I enjoy it. The fun fact is I got married 2 weeks ago, but it is not the same bachelor party that Shirley mentioned. I just wanted to make that clear. And you can contact me at this.
Well, otherwise you should have known the story.
Well, maybe it was so crazy I didn't know. Okay, so I think that concludes the introduction. Maybe we can go around and everybody can say your name, who you are going to work with, what center, and maybe your research interest and a fun thing about yourself. So let's start here.
Well, one thing I have to. So I'm David. I am a PhD student at the University of Amsterdam. I work on machine learning for radio astronomy. And I'm going to work here with Case Wong and Shirley Ho at the CCA. And the fun thing is I recently learned rope climbing, and I really enjoy that right now.
Hi, my name is Matthias Müller. I'm from Vienna. I'm actually still in my master's. I read my master thesis about
Hi.
The room mics are on.
Are they on?
Yeah.
Okay. I'm in computational quantum physics, and here we'll work with Domenico in the CCQ. And the fun fact, after my bachelor's actually in physics, I worked 2 years for a sports betting company using ML to predict basketball matches, football matches, everything. Before then, I went back to study.
My name is Leo. I'm studying at the Max Delbruck Center in Berlin, and I'm interested in applying machine learning models to biological image data. And I guess in this summer school, I'm working with Barbara Engelhardt to do that on a mutational screen of CAR T cells. And the fun thing about me is I like to hike a lot.
I am Roy Friedman. I'm doing my PhD thesis now at the Hebrew University in Israel. My master's thesis and what I'm starting right now to work on is generative models for images. So I'm in computer vision and computer science. I'm going to be working with Sultan Hassan and Shirley at the CCA. Yes, the fun thing about me is I like making cocktails. So.
Andrew Ligaralde. I'm a PhD student at UC Berkeley. I study neuroscience, specifically interested in modeling the visual cortex with machine learning. And I'm working with Suyan Chung at CCN. And my fun fact is that, yeah, I guess on the theme of basketball, I have a current bet on the NBA Finals, and the loser has to spend 24 hours in a Waffle House. Yeah, hope I don't lose.
Who are you betting for?
Warriors in 7.
Hi everyone, I'm Arthur. I'm a theoretical physics master student from Munich and currently writing a master thesis about graph neural networks for chemical applications, so like molecular dynamics predictions, those kinds of things. And otherwise, I'm working with Domenico here at CCQ, so doing like renormalization group flows with machine learning. And well, a fun thing about me is that I lived my first 18 years in a very, very small village. And this whole New York thing is still rather radically changing for me, even though I studied in Munich, but New York is a different number.
Hi, I'm Amaya. I'm an incoming PhD student at MIT. I'll be working with Miles and Shirley at the CCA on Dublin's prediction and cool things in physics. A fun fact about me, I really like enjoying tennis, but I can also play badminton. It's kind of a rare combination. But, yeah.
Hi, I'm Thomas. I'm a PhD student in Munich. I work on astrophysics, planet formation actually. I mean, yeah, I hope to learn a lot about machine learning applications to our field, and of course to apply those machine learning techniques. I'm going to work with Miles and with Shirley. Fun thing is I was actually here 4 weeks ago to visit Phil Armitage, and I really didn't expect to be back so fast. So yeah, that's fun.
Okay, hi, I'm Elena. I'm also from Munich, from the University Observatory. I'm doing there my PhD, and I'm mainly interested in the early phases of star formation, so the fluid dynamics and the filamentary structure of the interstellar medium. And here I'm going to work with Miles and Shirley at the CCA. And a fun fact about me, I like to play handball. I guess that's it.
That's so interesting. We're both from, you're in the same office.
Yeah, we're in the same office.
Yeah. Yeah, so, okay.
Hi, my name is Akihiro. I'm a PhD student at NYU here. And I'll be working with Professor Alex Williams. Fun fact, I like hiking and camping and like running.
Hi, everybody. I'm Juan. I'm originally from Uruguay. Now I'm a first-year PhD student at the University of Pennsylvania. Before my PhD, I spent some time at Stanford doing like ML for genomics. Then I got tired of dealing with all the different formats that are in genomics, and I moved to some more theoretical stuff. And fun fact, well, I'll be working with Robert Grower here. I'm not sure what the CC something is. And fun fact, all my life I wanted to be a soccer player, and I failed miserably. So this is the best I could do.
Hi, I'm Michael. I'm from Greece, from an island called Rhodes. And yeah, I study in Paris. I'm a PhD student at Polytechnique. And my research is focused on graph neural networks. Yeah, like, yeah, these months usually I'm enjoying the sun in Rhodes, but New York is nice.
Fun fact.
That's a fun fact.
Hi, my name is Fabian. I'm a PhD student at the University of Melbourne, but I'm also, as many here, from Germany originally. And I also lived for like the last 2 years in Berlin due to the pandemic and travel restrictions. And what I do is I use machine learning for turbulence modeling. So, and I also work with Miles and the CCA. And yeah, I'm really interested in symbolic regression as well. So to make things interpretable and also implementable if we would, insert turbulence models in solvers and stuff like that. And yeah, in general, just to also make neural networks more robust and more generalizable. And yeah, fun fact, I like to travel a lot. I like to collect country points where I watch football matches. So I like to travel around to see football matches in a lot of different places. Dortmund.
That one is tough.
So yeah, I guess I got some friends over there in Munich.
In the back.
Hi, my name is Caesar. I'm at Stanford for a PhD, and I'm doing quantum information theory and machine learning. And generally, in machine learning, I'm interested in generalization of machine learning models. So adaptation methods and domain shift problems with machine learning. And I'm working at the CCA with Arnivan.
Oh yeah, fun fact.
Oh yeah, my fun fact is I do sports, I guess. I like sports.
Okay.
I'm Mahalet. I'm a first year in the Stanford physics PhD program. I'm interested in cosmology and structure formation, large scale structure formation. So I'll be working with David Spergel at the CCA applying machine learning to this. Fun fact, to add to the German representation, I was born in Germany, but I'm not German. And I spent a year there when the pandemic first started.
Okay, thanks everyone.
Well, let's say that we are sponsored by the German government.
So third copy, I guess we just do the first lecture and then I copy that. Okay. So I will be giving the first lecture on introduction to machine learning. So for many people, I think this will just be like a very basic review, but I think it builds character. Okay. And there will be a short lab at the end. So if you have your laptop, you could do it on that.
I think it might be worth mentioning that people have very vastly different backgrounds. So some people are experts in the sciences and are new to machine learning. Some people are experts in machine learning and they want to apply it to sciences. So if you have a question and it seems like everybody else understands, just feel free to ask, because again, everybody's backgrounds are different.
Yeah, and I think it's also good if you help each other learn stuff. Like if you're an expert in something, someone else is new to that area. I think it's always good to kind of just help answer their questions. Okay, so this is our syllabus day. So we have 2 weeks of lectures, as Michael explained. So we have a final written exam on June 20th. Okay, so it is, very important. Like this is we're doing a public service, so we expect you to take it seriously. So if you get less than 70% of the exam, you get kicked out of the school and you have to pay for your room. I'm kidding. There's no exams or assignments. Just learn as much as you can from the lectures, and from your research project. We're not going to kick you out. Don't worry. Yeah, and we will have like a poster day in the first week of August, and you can present some of what you've worked on. Okay. Yeah,
There is a chat.
that's. I think it's just Shirley. I think Shirley said something. Yeah. Yeah, she'll be late, but she'll be there. She'll be here. Yeah.
So for the poster day, this will be like the results from the stuff we did in our workshops, or
on your project.
Yes, very good.
Yeah. Yeah, and there's no exam. Just
But you do have to get at least 70% marks. Whatever that. Fill out the page.
Okay, so I wanted to give just an overview of the PureML lecture series. So today I'm going to do, it's really small. Okay, I'm doing Introduction to Machine Learning. We're going to have Rob Gower doing first order optimization after coffee. Tomorrow we're going to have stochastic gradient descent, linear models by David Hogg, and then Intro to Deep Learning by Wanda. So Wednesday, we're going to have our first, our two kind of invited speakers. So Barbara Engelhardt from Princeton going to Stanford. She's going to talk about dimension reduction, and I think applying it to biology. Mario will talk about automatic differentiation. And you can see I've kind of made this tech tree and put way too much time into it. And so that will be automatic differentiation. And then we have Jan LeCun to be decided. His talks are always fun. And then, so June 9th, Thursday, Dan Foreman-Mackey, I think we'll have someone else do his virtually. I think his partner got COVID, so he can't come in, obviously. So someone will introduce Gaussian processes, MCMC, and then Stefan Malat will do kind of mathematical models for neural networks. I think he'll talk a lot about wavelets. And then I will again, you'll be forced to see my face again on Friday, symbolic regression. Okay, and then, so next week, so again, this is like the pure ML slide. We're gonna have more applied ML the second week. Introduction to geometric deep learning. So that's like graph-like data, deep sets, graph neural networks. Alex Williams will talk about introduction to statistical learning and matrix factorization. Then we'll have Kyung-Hyun Cho from NYU, big NLP person, on next Wednesday. Mary Lou will talk about generative models. And then finally, I think that's it, right? But yeah, we'll have Yuling Yao talk about Bayesian model selection on that Friday. Okay, so for applied ML, we're going to have, so there's actually like this really nice quantum series. So this is from Giuseppe Carlio and Javier Moreno. Yeah. So they're going to have this quantum series. And Anirban will talk about dynamic mode decomposition and kind of learning dynamics. We'll have Noam Brown, another invited speaker, talk about ML for diplomacy. I think, where is he talking about poker?
I think you'll be diplomacy.
Diplomacy. Yeah, both ones are really cool. Yeah. And then we'll have two more quantum talks. Wow, on that Friday. So variational MC for quantum and state reconstruction, and Siying Chung will talk about geometry and biological networks. We'll continue the quantum series. So Javier will present on fermionic wave functions. Mitya will talk about ML for biology in general. Shirley will talk about ML for astrophysics on Tuesday. And then, so finally, we'll have deep learning for genomics on the Wednesday, and then Thursday, the final quantum one. This nice, really nice quantum series. I'm so happy they did such a big series. Okay, so that's the kind of syllabus. Any questions about your, like what's on the final, anything like that? Okay, so this will be, I'm going to give an introduction to machine learning just to bring everyone up to speed. This is going to be basic for many of you who've done research in ML. but as I said, it builds character. So machine learning is basically a way of translating problems into algorithms. So, or you're translating data into algorithms. So computers are very good at performing logical operations quickly. So if you have a processor, it can multiply numbers, add numbers very quickly. The problem is, many problems, we don't know what the exact sequence of logical operations are needed to solve a problem. I don't know how to get my computer to do something, but I have data. So I can use machine learning to find the correct logical operations to solve that problem. So if I want to divide these numbers, for a computer, this is very easy. There's an algorithm to do this. But if I want to ask you, okay, what is an algorithm to detect a cat's face? It's hard, right? Like, I don't know how to put this in algorithmic terms. It's not obvious what the sequence of logical operations is. So this is where machine learning comes in. So it's a way of kind of translating example data into an algorithm and kind of using these parts of the computer. So you can use machine learning to solve your problem if you, one, you have a well-defined problem. So you can't ask it, what is the meaning of life? You can't ask it, how do I make money? Those are not well-defined problems. If you can write down a closed form expression to kind of minimize or maximize, that is a well-defined problem. The second requirement is you need to have or be able to generate many examples of your problem. Lastly, your machine learning model, it needs to be flexible enough such that the desired function kind of fits within your model. So it exists within the function class, is how you could say it. So supervised learning is, I think, the main type of machine learning, especially in the sciences. We want to map input to an output using some flexible model. So input data, and this is called the label or target. So we have many examples of input data. We have many examples of the targets. So for example, like a molecule, map it to a number, or a sequence of DNA into a number, or text. Those are all supervised learning problems. And you want to find a model that solves this problem such that your prediction error is low. So that's supervised learning. You have examples of targets or labels. So for example, like if you want to minimize the mean squared error, you could have some function f of x, and you want to match it with y. And you try to minimize the mean squared error of that prediction loss. So that is a supervised learning target. By the way, feel free to ask questions throughout if you have any. I like interactive talks. Makes me feel sane, like I'm not just spouting gibberish. Okay, so the other kind of machine learning is called unsupervised learning. In this case, we don't know what the true target is or the true label. What we have instead is some, we have a optimization target that doesn't need a label. So for example, say I have this data set that kind of exists in a 3D box, and I try to learn a compression of this data. So say it's in 3D and I learn a compression to 2D such that I can map backwards. That is kind of an unsupervised problem. And you can see how it kind of unrolls the data into this nice 2D manifold. So that is an example of unsupervised learning. In this case, this is like an auto-encoding problem. So there's two types. So within like supervised learning, unsupervised learning, there's also regression and classification. So classification is a type of supervised learning where I want to predict the class of an input. So for example, I want to model the probability of some input being in a class, like a cat or a dog. So, for example, if I have an image of a cat, image of a dog, these are represented as 3D tensors. So, like, how much red is it? How much green is it? How much blue is it? And then I have X, Y dimensions. So it's like a 3D tensor. Maybe my model would take this and predict class probabilities. So it predicts, okay, it's a really good model, 99.9% cat, 0.0 or 0.1% dog. And so these are the class probabilities. So it's a good classifier, unlike every classifier I've written. It's good. So one example of this is like a linear classifier. If I have a scalar input, like a real number, I can multiply it by a parameter, add a parameter, and then map it through this tanh function. That will map it between -1 and +1. So maybe my two classes are like -1s and +1s. And using this mapping, I can put X into those two classes. So that's called a linear classifier. So yeah, in the case of this cat classification example, when we're fitting this model, we try to optimize the following expression. So this is the first part. Let's say my true label is YK. So this is like YK equals 1 if something is true. My model predicts the probability of it being true. So F of input XK. And this term is basically how much the data in my model match up. And then I would add this term, which is like, if YK equals 0, this term would show up. And then this would be the probability of my model predicting the other class. So maybe I would try to maximize this over the parameters, and that would give me like an optimal classifier. Any questions about this? We are going a bit fast, as I think coffee starts at 10:30. Any questions? Okay. Oh yeah, question, yeah.
You mentioned a flexible model before. What is that?
So, oh yeah, that's a great question. So I think this will be covered tomorrow a bit by Rob and Wenda, but I should have said something now. So the flexible model might be something like a neural network, or it might be like the function I showed with like tanh of ax plus b. That is kind of a model that can express many different functions. It's basically like any function you can imagine is like stored within my flexible model. Like I could express it. I'll give an example of a neural network actually. I think now, yeah, okay, perfect. So this is a really fun interactive website called Tensorflow Playground. Maybe you've played with it before. Basically, what we want to do, we want to put the orange points into the orange region and the blue points in the blue region. Okay? So orange represents -1, blue represents +1. The way we do this is we map the x coordinate, so that's this, and the y coordinate, which is this. We map them through this function. So tanh, it's kind of like, so tanh looks like this. Yeah, we can draw on the walls. I hope so. So this is -1 and +1. So tanh looks like this. Like if you give it really positive input, it's going to go to +1. Really negative input, it's going to go to -1. So it's a way of taking some arbitrary large or small input and mapping it into the classes. So let's train this. So I'm going to hit train. Okay, so it's training, training, training. And you can see these coefficients are blue, which is plus 1. So this one is 1. This one is 1. So now it's tanh of x1 plus x2. That is the model that has been fit. And you can see it nicely covers the orange points in orange and the blue points in blue. Okay, now let's do something more complicated. So this is a ring of orange in a blue circle. We're going to use the exact same model. So let's see if it'll fit it. It does not. It sucks. It doesn't fit it. And the reason is because it's a linear model. It's not flexible enough. It's not expressive enough to find that surface. So here's where a neural network approach comes in. Rather than predicting just x1, x2 predicted output, I'm going to do this recursively. I'm going to repeat this process. And now what I'm going to do is I'm going to predict 3 intermediate values. So let's call these y1, y2, and y3. So y1 is equal to tanh of ax plus by, bx2. And y2 is this one, and y3 is this one. So these parameters are different, right? Like, so a and b are there. And so it's kind of like it's predicting intermediate values, okay? So it's kind of like the last example I showed, but it's modeling that surface, but here. And it's doing it 3 different times. Then what I'm going to do is once I predict these values, I'm going to use the same model with different parameters. And I'm going to, again, run it through the tanh function. So you see it's basically equal to, this whole model is equal to tanh of gy1, hy2, iy3. And those values are equal to these, 1 by 1. So there are 1, 2, 3, 4, 5, 6, 7, 8, 9 parameters. And so those are, you can see them here. Right, those are all the parameters. And so now let's click fit. Okay, so yeah, so it does much better. You can see it actually finds it. And we can look at how this works. So if you look at these intermediate values, it's a bit hard to see, but you can see these are kind of like planes. Like this one is like a plane here, right? It's like this. This intermediate value is like a plane here. This intermediate value is like a plane here. So, and the second part is this part of the network kind of adds them together. Like it superimposes those surfaces and it finds the output. So by recursively running this logistic regression, we can model more complex surfaces. And this is how you get an expressive function by repeatedly applying this formula. So this is basically like a neural network. And I'm sorry to say, but like a lot of deep learning research, you literally just like stack them. You just go down, like you just have a lot of intermediate values. Like the deep in deep learning, you just go deep this way, right? Like that's literally, there's like major papers are just saying like scale is the only thing that matters, and you just go that way. Like that is basically a neural network. So you can see on the right, we have a more complex surface. We have this spiral of orange points, this spiral of blue points. So let's see if this more complex function can find it. And I'm not gonna, I didn't write down the equations because I'm not a psychopath, but you can imagine what they would be. Okay. Okay, so it's a little bit unstable, but yeah, okay. So it does get there eventually. So you can see how the first layer is like all of these different planes, right? The second layer is superpositions of like multiple planes that have stacked up. And the third layer is even more. And it's kind of like stacking up layers, which are kind of like superpositions of planes. And this is how you can express very complex surfaces with, in this case, a deep learning model. Any questions about this? Well, yeah, it's called Tensorflow Playground. Very fun to play around with on a Friday night when you're bored. Play around. Okay, let's talk about regression. So in the previous example, I showed you how we can predict probabilities over classes. Regression, we want to predict a continuous quantity. So for example, a line of best fit, that is literally machine learning. Like we have this model. Our model in this case is AX plus B. That is our model. Two parameters A and B. Our loss function in a line of best fit problem is the sum of the squared error. So yi minus f of xi. Try to minimize that. This is our data set. So we have xi is like how far it is that way, yi is this. So all those blue points are our data set. So that is a regression problem. We want to predict a continuous quantity. And like in practice, like some regression problems are 1D, so like in time series modeling, but oftentimes it'll have like maybe more input dimensions, try to predict one number or multiple numbers. So just to recap, in supervised machine learning, I have examples of yi. I want to predict yi, and I have examples of it. In unsupervised learning, I don't have examples. I have some input data, and I want to manipulate the input data in some way. Maybe I want to try to compress it or do something else with it. Classification, we talked about. So this is where you predict which class an input data point corresponds to. So that's one example, the tanh, and then you can imagine like just many repeated applications of that. We also talked about regression, so it's like predicting a real number, like a line of best fit. Any questions about this? Okay. So the last part before we do a short lab. So has anybody driven in a self-driving car? Okay, I don't know how popular. I've driven in like a Tesla when they have autopilot on, but not like full self-driving. So self-driving cars are built on machine learning. The input data in this case, so it's a regression problem, right? Like you want to predict the angle of the wheel. That is a continuous number. But normally what you do is you have these cameras on the car that records your input data. And another thing that people train with are human demonstrations. So if someone is driving the car and they're steering the wheel, you could have the machine learning model predict the wheel position based on the image. So you might learn on a training set, but the problem with this when self-driving cars first started is you would have a very, very accurate model on the training set, but it would crash on real tests. And so the problem is, in this case, you would have very accurate model on the training set, but when you see new data, it performs badly. So that is an example of overfitting. So in overfitting, say I have, these are my data points, right, the blue. The true function is the orange line. maybe my learned model is the blue line, right? So in this case, I'm underfitting, right? It doesn't look like the true function at all. So maybe I turn up the complexity a bit and I find the true function, right? So this is a 4th degree polynomial. Now I'm like, that's a good fit. Maybe I turn up the complexity even more, and now I am overfitting. So I go through every single data point, like it's very accurate, but it's not a good model. So the solution to this, which is, like I think even some ML researchers still fail at this actually, is to train, validate, and test your model. So you avoid this problem with something called cross-validation. So this is where you train on one part of your data set and you validate it on another part. You see the performance of your model on another part of your data. Like literally sometimes people will like mix up their data and they won't realize they've actually tested their model on the part they've already looked at before. So the one way to do this is this is like your training data. So if these are like maybe the points from x equals 0 to x equals 10, and this is like x equals 10 to x equals 12. What I would do is you'd split your data, you train on this part, and you test your model on this part. So this is called your training set and your validation set. And this is like, you should always do this in machine learning. You train on a data set and you test it on a validation part. So for example, in the line of best fit case, you would only train on these data points, but maybe you test on these. And the model is not allowed to see these during training. So, okay, a question you might ask is, okay, what if the validation set is like very small? And like, maybe I'm only testing on like these. Like, I don't know if that's really good. So the solution to that is something called 5-fold or n-fold cross-validation. Basically what you do, you cut up your data into 5 chunks, right? 1, 2, 3, 4, 5. Then I train on maybe 1, 2, 3, 4, and I test on this one. Then I repeat it, I train on these, and I test on this. So like you test on one portion each time, you train on the rest. And you just repeat this over all combinations. And that is a good way, it's called cross-validation. It's a very good way of testing the power of your model. So one other point is you should always, when you're training machine learning model, you should always leave out maybe like 10% or 5%, depending how big it is. You should leave out a part of your data called the test set. You should never look at this data when you are configuring your model or testing parameters. Don't use this during cross-validation. You should just like put it on a USB and hide it in a cave and come back to it at the end of your project. And that, so once you are finished your project, you can test on that data set, and that is kind of like what you report your performance on. So it's called the test set or the holdout set. Okay, so just to recap, like you have your, so this is like a pipeline. I have my training data. So I have many examples. Maybe these are like images, or it's like a state of a physical simulation. And the Y could be like the energy, like I want to predict the energy. That is my training data. This is my model. In this case, this is a linear model. And then I try to minimize a loss function. So in this case, this is like a regression loss. I want to minimize the mean squared error prediction. But you could also have like a classification loss, or there's many others. And then for training, you generally want to do something called cross-validation, train on some part of your data, test on the other part, and repeat this over all sections. Okay, so that was my really fast introduction to ML. This was really basic. The other lectures will be a bit more kind of detailed, but I just wanted to set a base for everyone. And I thought we could do this regression lab. So this is just like a NumPy tutorial in Google Colab. And I think this will also be a good introduction to using Colab. So if everybody can go to this website. Let me know. Okay, people are still answering it now. So Google Colab is basically like Google Docs or Python notebooks. It's actually really useful for deep learning. My most cited paper was made entirely in Google Colab, so it's not like just some like educational tool. It's actually really useful for research. It's really useful for sharing code with other people and just training in the cloud. So we should be able to get everyone pro accounts. Siavash, do you know how we can actually set that up? Okay, I'll talk to Kristen after. Yeah, the pro account just basically gives you better GPUs. If you've already bought it, we can probably reimburse it. Okay, so once everybody's good, this is basically going to be, like, I'm not going to walk through it. There are parts of this notebook that you need to complete. I have the instructor's notebook, and I'm not going to show you it unless you ask nicely. And just go through the notebook and try to complete it. For many of you, it would be like you've already seen these things. For others, it will be new, and I'm happy to help out on any of this. So yeah, let me stop the share, and I'll let you work on this. And maybe yeah, I'll just go around and help anybody who needs help. And I think coffee is at 10:30, so maybe the last like few minutes I can go through the solutions. Look at the infinity. Session. Yeah, let me know if anybody needs help.
Fortran does not compile.
Okay. Where is it? Like, I mean, it seems like it locks into the. go to the solution. That's why I'm not in cybersecurity. Okay, so it is coffee time. And then after coffee, come back at 10:50. Okay, 10:50. Yeah, so David Fergal is the president of Climate Foundation, and he's going to give us a short speech. At 10:50. Okay, so we can take coffee break. Yes. Feel free to look at this.
So, hi everyone.
Thank you so much.
Let me, maybe I'll even share screen. Why not? Because my name will be on the screen. Right. So I'm Robert Gower. I'm a research scientist in CCM, the computational mathematics group. I'm sorry I'm not there with you today. I got COVID about 9 days ago, and I'm still testing positive, but only barely. So I may show up soon. We'll see. So I work in optimization mostly, but now over the last 5 years, I've been leaning towards optimization for machine learning. So how to leverage the structure, the properties of different machine learning problems and optimize them faster. I'll give you a lighthearted introduction to machine learning, very lighthearted, probably too light for most of you, but since I'm the first lecture, we might as well take it easy. Maybe any questions for me? I don't know. Is there? I probably should. It's too early for questions, maybe. So I'll talk about these things. I'm going to give my very lighthearted intro to ML, my notation. I'll talk about gradient descent, stochastic gradient descent. Can you see my mouse pointer, or is that not a thing?
Yeah.
You can see it. Okay, so you can see this. Probably small. Also, all the material you'll see, all the slides, there'll also be some plots in my slides. You can generate them from code, and you can find the slides on my webpage, which is this here, gowerrobert.github.io. I also have exercise sheets. Now, my idea is I put the exercise sheets online. I'll tell you which ones I think you should do. The solutions will go up the day after. And the idea was that I would be there in person, and then you could, ask me about how to solve them, or if you get stuck. But I'm not there, so it's not sure how well this is going to work. But we'll see. Okay, so here's my lighthearted introduction to ML. So when I wrote these slides, it's already been a few years now. The kind of references I used in particular was this book, Understanding Machine Learning from Theory to Algorithms by Shai Shalev-Schwartz and Shai Ben David. If you're looking for a short and sweet introduction, I like this book. It's only 300 pages long, and yet it covers pretty much, in theory, it covers every topic, major topic in machine learning, of course, only briefly and very densely. For optimization, there are many good books. This is maybe one of my favorites by Stephen Boyd, and I will talk a bit about convex optimization. So this is a good reference as well. Okay, so on with my lighthearted introduction of ML. So machine learning is about doing tasks which are relatively simple for us and hard for computers. So the first task is, can you identify there's a cat in the photo? Right. So you're given the input. So this is the input, the image, and you have to output yes or no. So this is very easy. It's yes. This is still yes. This is actually a raccoon, so it's no. And here we have one more cat. So just to start building up the language I will use, I think of the image, I call it an input. Sometimes I refer to it as the features, or sometimes it's a little x. So all this is the same thing. And what we are doing is we're passing in our brains the image through a map H. And somehow we're able to answer yes or no. So, and this answer, I will call it the Y as the output, the target, and actually I often refer to it as the label. as well. So it has many names. In fact, I almost always call it a label, despite what I've written here. So the objective is to find a map H that takes the input and outputs the correct label. How do we do this? I'm going to show you the supervised learning notation for this. First, you collect a bunch of images. So here we have all these images mostly with cats in them. And I call the first image x1, the second image x2, all the way to xn. And we label them by hand. We sit there and just see if there are cats in them. So it's y1 equals 1, and that means yes. And y3, the raccoon, equals -1, and that means false, means no. We collect a bunch of labeled data. We pass it to, let's say, a training algorithm that's going to try to learn something from this. And then it's going to spit out our map, our model H. And the hope is that after it's done all this, our model H is going to be able to give labels to images it's never seen. So here, H applied to the image of a bulldog should output -1. Okay, I said this was lighthearted, but at least there's some notation. Right, so unfortunately, images are actually highly complex inputs, so they're quite hard to talk about in terms of some nitty-gritty details. So I'm going to change the example completely, and now we're going to think about trying to guess the height, someone's height, based on their age and sex. So I made this slide. I can tell because I'm number 1, so it's been 5 years since I made the slides. So there are 2 features in the inputs, x1 and x2. x1 is sex, x2 is age, and the label, the output we want now. I won't say label because it's a real number, but the height is the height of the person. Right. So the first thing you need to do is, to begin to find a model or map that goes from inputs to outputs, you need to parameterize the model. So you need to come up with parameters here, and I'm using W, that are going to describe the family of functions that we can choose from. Because you can't just choose any function. There are, the number of functions that different functions exist is a huge infinity. It's not even like a regular size infinity, it's a huge one. So let's just start with something simple. Let's say that we're going to try to make a linear model. So what that means is going to take x1, the sex, and x2, the age, and it's going to output w0, which is a constant we can fit, x1 times w1, so we get to multiply the sex by a constant, and x2 times w2, so we get to multiply the age by a constant. And I'm also going to use another very standard convention in machine learning, where I'm going to introduce a dummy feature, x0, I'm going to call it 1, just so that it allows me to write this entire function here as the inner product between a vector w and a vector x. I forget the name of this trick. Is it the bias trick? Anyone know what this trick is called by creating a w variable, x0?
It is the bias, yeah.
The bias trick, okay, yeah. Oh, I forgot that. All right, so now to complete my example, I'm just going to say, well, now we've got the model. Now we need to somehow use the training data. So what's one thing we could do? We could just take the output of our model, which is here, h of w on xi1, xi2, and we could subtract the actual height that we know and take the squared difference. So the further you are from the true height, you're doing badly. Okay, so let's see what this looks like. I've plotted here just height versus age, because I fixed the sex, let's say only for males for now. And this is kind of like the answer we would like. It's a straight line. It's naturally a straight line because we're using a linear model, and looks good to me, looks fine, sort of. So why did we do this? Okay, do we have to use linear? No, we use the linear model now, but nothing prevents us from using polynomial models, which I think I maybe misspelled. So we could use squared interactions between xi and xj, between different features. And this would allow us, to do parabolas and other conics. In fact, we can use pretty much any directed acyclic graph for a neural network. So here we have two inputs, x1, x2, and we can feed them into intermediary functions, which I've labeled the output as v1 to v4. And v1 can be sort of any linear combination of the features x1, x2 passed through some nonlinearity. Here I've chosen sine for no apparent reason. v4 is now 1 over, sort of like a logit function almost. So you're free to choose sort of anything. But this here comes in the modeling of you understanding what you're looking at, what's the phenomena you're trying to capture, and who knows what that is. So final piece of notation, still a few more pieces of notation left. Why did I use a squared loss? Well, I use a squared loss because it's regression, but in general, there are many losses. So you can define, let's say I'm going to call y of h is the output of our hypothesis model. I use h to, sometimes I refer to it as hypothesis. I'll almost definitely stop referring to that later on. So, but it's the model.
Well, yeah. Can we take a break now?
Yeah.
Sorry.
No, it's fine. It's good at any point.
Here, we just told you we just met in here.
Who asked me about machine learning? Yeah, so I'm David Spergel. I'm the president of the Simons Foundation and wanted to welcome you here and first say just a little bit about the Simons Foundation and this program and some of our goals here. So the Simons Foundation was founded by Jim and Marilyn Simons about 27 years ago. Jim Simons is a mathematician. He's the Simons of Chern-Simons theory. So did some important work in mathematics. He then decided he was interested in how the economy works. He set up a hedge fund called Renaissance Technologies, which is the most successful hedge fund in Wall Street. It averages 50% return a year and has done that for the last 30 years. And if you stick e to the 0.5, e to the 15 in front of most numbers, it gets big. Jim, that actually doesn't keep reinvesting at all, but it's all complicated. But anyway, he's done well. And he put in his wife, Marilyn, put more than half their money aside into the foundation, which supports basic research in math and science, the work in education and outreach. So among the things we do is we support Math for America. That's the building you're in here. Math for America supports 1,000 high school math and science teachers and 400 city public schools with a goal of teaching more math teachers and more science teachers in the public schools. It provides a $15,000 a year supplement to their salary, which helps keep them in the schools. And it brings them together as master teachers to be able to work together. Other things we support in outreach include Quantum Magazine, which won the Pulitzer Prize this year. There'll be a party on the 14th to which you're invited to, celebrating the Pulitzer. We also support a lot of work through grants in areas ranging from autism to oceanography to math and physics. We give out about $300 million a year in grants. Some of that is here in New York, but it's actually worldwide. We're supporting institutes in now from India to Africa, all over Europe, many places in the US, other parts of Asia. We're supporting Ukrainian scientists who have had to flee. We have a very broad range of things we support through our science program. And then one of the things we support that you'll all be part of is the Flatiron Institute. And the Flatiron Institute is an institute with about 200, growing to about 250 people. We have 5 centers. It was founded 7 years ago. And so it's odd in that for some people, it seems like it's been around forever because you come as a graduate student and you think it's always there. But, we didn't move into that, 5 years ago, we were not in that space. We were in some temporary space. Then we only had a few of the floors as they were doing construction. So it's really grown. We've got to create it, which has been incredibly exciting over the last few years. And we have the programs in computational biology, which was the first one, computational astrophysics, quantum materials, and the two newest are mathematics and neuroscience. So computation, those, because the newest, we haven't even filled out the staff yet. We're adding and growing. And our goals with these centers are to attack problems that demand more resources and more time, something, and more methodology than people have been able to address as individual units at universities. Oh.
If you stand in front of the projector screen, online people can also see.
Am I on now? Oh, good. Okay. Now I stand in front of bright light, but they can at least see me online. So that's what we're trying to do with Flatiron. This works, yeah. Okay. No, not directly in the bright light. And one of the things we've been doing at Flatiron that's been really exciting is we've got a lot of people across the centers making use of machine learning. I think that machine learning, at a minimum, it will turn out to be a useful tool that will help us address a number of problems in science. It could turn out to be as important as something like partial differential equations, where it is a tool that we use in a fundamental way to address problems we couldn't have addressed otherwise. I think it is still early days for us to discover how powerful it truly is for our science problems. It'll be at a minimum a good thing, but it could be truly a great revolutionary thing. And you are entering this area at just the right time. And the hope is here that we'll be engaging in problems across the sciences. And what's exciting for us about this summer program is that it goes across Flatiron. We've done these programs before, but they've been focused on individual centers. And now the fact that we're doing something Flatiron-wide represents, I think, a great opportunity for us, for you, and a sense of where we are intellectually. And I think we'll all enjoy it. To give a sense of the excitement about machine learning, as Shirley mentioned, my morning meeting before coming here was with Mayor Adams, our new mayor, and we were talking about things that we do for the city. There's some things we want the city to help us with. And one of his asks for me was they have these very large data sets that they put together in everything from policing to energy use. And they feel that there are machine learning tools that could be helpful for them in addressing some of the problems. And he asked me, do we have people who could help them? I said, maybe. That we have lots of scientists with useful tools. One of the things about scientists is you can give people problems, and that's really up to them whether it excites them. So I said, come to us with problems, I'll try to connect you with them. So, the mayor of New York was asking me about machine learning earlier this morning, give you a sense of what the excitement field. This should be a fun summer. I think there should be exciting opportunities here to learn through the program, to work with your mentors, to work with people at the center, but also get to know the other summer students. We have a total of 100 summer students here in many different programs. The National Society of Black Physicists have a program across the centers with a lot of undergraduates. We've got graduate students and undergraduates working in individual programs with the center. We have summer interns working with Quantum Magazine, with autism work, with our Civic Affairs office. So you'll all be together at lunch and dinner. We'll have a bunch of social events. So I hope you not only enjoy the program, but more broadly enjoy summer assignments, and summer in New York City. The summer is an incredible, exciting time in New York City, and you should certainly do your work, but there are also opportunities to hit the bars or hit theater, and there's a lot of free theater in the park. A lot of free music going on in places like Little Island. I encourage you to open up New York Magazine, the front section, just lists free events in the city. And a lot of great museums, and just walk the streets and soak up the energy. And have a great summer. And I'll be somewhat involved in this program myself. I've been interested in this area, working with Shirley and Miles in particular. And so I'll also not only be engaged with my hat as organization president, but as a scientist who sees this as powerful for the rest of the problem. So welcome.
I've got 2 minutes. Please wear your mask when you're in a room like this. I have extra mask. This is Silence Foundation policy, actually. So anyone who don't have mask can pass it around. It is also because there's a lot of people who test positive. I didn't want you guys, this is the last time I see all of you at the same time. So, because otherwise you get quarantined for 10 days. And everyone, if one of us tests positive here, the whole room gets quarantined, like everybody. So, for your sake and our sake, please wear a mask when you're around a bunch of people. So the rule, I don't know exactly the rule. I just wear it all the time, except I'm alone in my office. Is that the right rule? And when you eat,
yeah. Effectively, yes.
effective.
Yeah, I think the typical thing is if you're in an office and the office space can really adjust. But that's basically like all the common spaces you're supposed to wear.
Yeah, if you don't have extra, there's extra at the front door of every places we go into in Spanish 2 and Spanish on here. So, and we can also give you extra mask and extra tests if you don't have them. All right, thank you. Because there's lots of people. I think the gravitational waves workshop, the first day everyone came, the last day a different person because of COVID quarantine. We can just have a dinner with the group and then. So yeah, try to stay safe. Also, you get to go hang out in New York City more if you're not being quarantined for 10 days straight, right? Thank you guys. Sorry, Robert. Thanks.
Yeah, that's all right.
Good for you.
Okay. So let's pick up again. So what were we talking about? So I was just introducing now notation of loss functions. We could use different loss functions. In my very simple example of heights of people, we use a squared loss in regression. But now we can go further. If I abbreviate the output of our model by YH, we can introduce we can use any loss function, which is this curvy L here, that takes the 2 labels, so the one pre-model, the true one, and somehow compares them, and it outputs a positive number. And it's a loss function. The larger the positive number, the worse we do. Okay. Typically 0 is kind of like the best. And this gives us this more general training problem, which is we want to minimize the average of all data points of our training set, the loss between the output of our model and the true label. Now, I will add this disclaimer several times, but all of these things, the model, the loss, can be informed by the physics of your problem, by the statistics of your problem. You can make statistical assumptions on what kind of data you have, if it looks like Poisson, if it looks normal, and this would suggest to you what kind of loss functions and maybe what kind of models, but I'm not going to talk much about that. I'm going to talk about this from an optimizer point of view. So all this notation, all these things have to be more or less given to the optimizer, and then we're going to solve the problem. Right. Loss functions are typically convex themselves. The model itself, H is not, but the loss functions are almost always convex functions. So we'll see a bit about them later. So let's have a look at some different loss functions. So squared loss, just a simple parabola. I'm plotting this because the loss takes two inputs. It's hard to visualize. So I'm fixing one of the inputs, the true label to be 1. Okay. So there's the parabola. In more sort of ML theory, when we want to prove things are modelers, we actually use often the binary loss. The binary loss is this very brutal loss that says that if you have the correct label, if YH equals Y, you're exactly the correct label, you have no loss. Otherwise, if you have the wrong label, you have loss 1. This is actually a pretty terrible loss in practice. It gives you no signal if you're close or far from the solution, but in theory, it's often used because it's accuracy, right? Which is it tells you how many times you got the right answer. You could also use asymmetric losses. So here's the hinge loss, which only penalizes on one side. So here, for instance, you can see that you have this blue line increasing linearly to the left if you're wrong, and on the right, it doesn't care. And that often happens when you have sort of a problem where you're in the correct, you only care if you're too far to one side of the label. And being further to the right in this case means that this is still the correct thing. We're fine with that. So the classic example is having points in 2D and you want to separate them by a hyperplane. If you're on the right of the hyperplane, you classify it one way. If you're on the left, you classify another. If you're too far on the right, it's not a problem if you have the right label. Okay, I often have little pauses. I think I won't do this because I'm doing this online, but I often have pauses and ask people to draw or do different things, exercises. But I think I'm just going to walk through things slowly instead of asking you all to write down little exercises, since I'm not there to help anyway. Okay, the final piece of notation is a loss function enough. How have we done? Is this all the notation that's required? Does anyone want to take a guess if there's something fundamental missing? Just think of this as an opportunity for me to know that the microphones are working, and you can say literally anything.
Can you hear me?
Theory? What? Theory? Is that what I heard?
What do you mean by the question?
Oh, well, it is quite an open question, to be honest. So the question is like, so let's see how far I've got. Let me reframe the question here, looking at this problem here. I'm calling this the training problem, which is what we will try to solve in optimization to train our machine learning model. Am I missing any key concept or element from this training problem that you would, need in practice?
How do you get to the minimum?
Can you say that again, sorry?
How to get to the minimum, I guess.
How to get to the minimum? That's true. Absolutely. We're completely missing that. I will go over that in the next few hours. But there's one other thing that's sort of missing as well. That's even beyond optimization. Before even trying to solve this problem, I haven't got the right problem just yet. We're still missing one thing. But just a question about microphones. Before, I could hear everyone talking individually to everyone. Are they stealing microphones?
No, maybe we need to open the table, please.
I can hear you now very clearly.
When you talk, just push the button so the light goes green.
If it's not green, they would not hear you. Because now his is green.
So should we turn all of them off?
No, just turn on when you're talking. Otherwise, they hear your.
That was good because I heard you very clearly. The gentleman who said turn them on. Yeah. Okay, so I'll introduce the last structural element in what I call training in the training problem before even optimizing, before even trying to solve this. And the question comes like, what happens if we don't have enough data? Is there a problem with me just trying to fit a notion of loss between the output of our model and the true labels? What could go wrong? Let me give you an example. Let's consider this training data set, which are these blue points, which I made pretty much in Paint. Y is our label, X is our feature, so this is a regression problem. Let's say we use a squared loss, and let's say we start with a linear model. Okay, this is the best linear model that fits the data. Okay, it's awful. What we're missing is I chose a bad model. Let's choose a good model. If I use up to the second order polynomial, this is a pretty good model. You get this parabola, looks pretty good to me. But what happens if you don't know? You can't visualize. This is 1D data. We can see it. So let's say you start making guesses. You're like, well, I can turn down the training. The training loss gets better if I increase the order of the polynomial. A third order polynomial, the training loss gets down, and now I'm going to go to a ninth order polynomial, and the training loss is 0. I fit perfectly every single point. So in case I didn't make this clear, sorry, the orange line is the output of my model of this H. And now I'm using the up to the ninth order polynomial. But clearly this is a terrible model, right? Look at how it's like bending around every single point. This is classic overfitting. And so to avoid overfitting, what we can do is add a regularizer. So a regularizer is anything that sort of punishes complexity in our parameters W. So again, W being the parameters of our model H. From a statistical point of view, if you make statistical assumptions on your parameters, then the regularizer is the prior, acts as the prior likelihood over your parameters. But from my perspective, someone's just going to give me a function that's R, capital R, very similar to the real numbers, unfortunately. It's positive. The bigger it is, the more complex, unnecessarily complex our parameters are. I'm also going to introduce, wait a second here. Yeah, I'm also going to introduce this parameter lambda. Lambda is just going to be a parameter, unfortunately, we often have to choose. The larger it is, the more interested we are in simple solutions. The smaller it is, the more interested we are in fitting the data. So we have one term that measures how well we fit the data, goodness of fit, fidelity to the data, you can call it lots of things. And the second term that penalizes complexity and stuff like that. But unfortunately, we have this parameter lambda. So this is also called, what do deep learners call this thing? Just slipped my mind. Does anyone know what deep learners call L2 regularization? They call it.
You're gonna love saying weight decay. Not exactly.
Weight decay. Yeah, it's weight decay.
That's the green button that you want to speak.
Say it again, sorry?
Is it called Tikhonov regularization?
Yes, it's also called Tikhonov regularization. That's exactly, yes, especially when it's in regression. People often think of linear regression plus L2, they call it Tikhonov. So that's great. That's a great answer. But in deep learners, they call it weight decay. And weight decay is actually specifically when you use L2 regularization with a stochastic gradient type method. It changes the update of stochastic gradient descent in a particular way where you have to decay your weights. You have to decrease them by a certain factor lambda. Controls trade-off. Okay, here we go. All right, so there are other regularizers you can use. There are all kinds of things, really. You can use just different norms. That's very typical. So instead of L2 norm, you have the L1 norm, which I didn't define, but it's the sum of the absolute values of the vector, or any other P norm, or TV norms, or entropy, and many things. So the cool thing about using regularizers, though, is that sometimes you can get the right kind of model without having to know too much about your data. So for instance, if you use an lambda that's just the right number, right setting for lambda, and an L1 norm, even if you choose a high order polynomial to be your model, the solution can be a second order polynomial anyway, because L1 norm actually forces a very sparse solution, the polynomial, and it can choose only the coefficients that matter the most. So you can end up having actually good models without having to have deep introspection into the data and knowing what order polynomial you had to set before. Okay, so now let's just talk about the ingredients I introduced, the notation. So I almost exclusively talked about linear models, but here we have it. So if you combine a linear model with an L2 regularization and an L2 loss, this is the resulting training problem. We call this ridge regression, or linearly scarce with Tikhonov regularization. And I'm sure it has many other names. This is a model that is, throughout all of science, linear regression with regularizations everywhere. Support vector machines has the same model, same regularizer, but uses the hinge loss. And this is support vector machines with a soft margin, if you've ever heard of it. If you've not heard of it, just take it as a definition here. I'm not going to show much more. Logistic regression, again, this is quite uninspiring because we're all using linear hypothesis and L2 regularization. But if you switch for logistic loss, then this is a good model for binary classification. You have two labels, true and false, like the cat. But this would not work on the cat images because cat images are too complex. Okay, so this is my ML overview, very lighthearted, very quick. My perspective of ML as an optimizer, which is an extremely one-sided, limited view of machine learning, but I'll give it to you anyway. Collect data. I talked about supervised learning, so I'm going to collect labeled data, x1, y1 to xn, yn. I somehow have to choose a parameterization of the model of the hypothesis function or our model. Somehow someone has to give me a loss function or I have to choose it. I forgot the other step. We have to choose the regularizer, but here it makes its appearance. And obviously you have to choose, unfortunately, tune lambda, and that's really annoying. And then you have to test and cross-validate, see if it fails. If it fails, you have to go back any number of these steps. But I won't talk about much of anything except step 4 from now on. Mostly because I don't know that much about the other steps anyway. So I'm going to talk about how to efficiently solve 4, and also theoretically solve it, which is maybe a bit different. How can I guarantee we solved it? Okay, so that was my lighthearted introduction to ML. It's very quick. Any questions so far?
I have a question.
Yes.
Can you hear me?
Yeah, perfectly.
Does the model include the regularization term, or is the model just the first term?
Yes, it's a good question. I might end up using the word model in a very overloaded way, as I think many maybe often does. So when I keep saying H is my model, even though in the slides it's always written hypothesis. So in this sense, if I call H the model, then the regularizer is not strictly speaking part of the model. But then if you think about the whole thing, in the end, this whole problem is going to influence what your W is going to be, what your weights are finally going to be. So many people might refer to this whole thing as a model of what you would like, in which case the regularizer would be part of the model. So this is just a long way of saying that the word model is highly overloaded and probably should avoid using it and give different things, different names.
Does that mean there's different, sorry, does that mean there's different values for lambda, or is that like a fixed parameter?
It's fixed before you solve the training problem, but how to fix it is not clear. That's actually difficult. So in one sense, there are different values.
Thank you.
I'm assuming that either played something wrong or it's left up around that illusion. So I just want to give it a 2 minutes.
I take a minute break when Robert's trying to reconnect with us. Yeah, we'll use the bathroom, come back.
Oh, did you?
Yeah.
All right.
Yeah, so, Miles and I will also help.
So that's sort of takes care of that. General.
Yeah. Yeah, we still.
This requires it's and for 11 cutoffs.
Yeah.
Go to the 11th floor, and get
It's great.
they're like full there.
I'm sorry about that, everyone. Am I back?
Hey,
That was totally my fault.
To the bathroom and coffee.
Yeah, we took
Bathroom break?
we took a quick break.
Perfect.
But they'll be back.
Great. Perfect
Oh.
timing, given that I dropped off. Yeah, I didn't plug in my laptop when it died.
Well, there was a causal relation between the two.
We send them to the bathroom so that,
Yeah.
we don't get sometimes they're back.
Okay, that's great.
Hey, Robert, this is really useful. I'm actually learning. I
Oh.
actually love to get your lecture notes. Like, I think it's a great way you teach it.
Sure, I'm happy to share. In fact, they're online. Hello, Jenny. Yes. See you good.
They're coming back, Robert.
Yeah.
Okay.
I'll get a drink as well.
I think we have. I think we have an idea.
It's gonna be useful.
Yeah, but I think all sent out the last. This was May 11th, so we have an email from me.
Thank you.
That's the other thing. That's enough. I'll come over. Go on.
Yeah.
Today. Yeah, there's some
This is here. The internships are. I'm done.
So someone just let me know when everyone's sort of back. I can more or less see. I can't quite know people are missing. And
I think we only have a couple missing, and then they're
Okay.
walking in right now.
Okay, cool.
I think we're good-ish now. We have maybe two more missing. That's it.
So maybe any question about anything so far? We got one good question about if the regularizer is part or not of the model, or
I had a question. I was curious about what you thought about like information theory regularization techniques. Yeah.
Right. Let me just sort of try and remember. I know you can motivate different sort of entropy-based regularizers through Shannon entropy regularization, but I don't know that much about it. But there's a dual edge, there's sort of a dual viewpoint where you can argue that, see if I can remember this, using the least amount of information possible can be seen as penalizing complexity. But I don't know that much about it. It's been a while since I read anything about it.
Also, there are some people that work on calibration of neural nets that use entropy regularization to obtain more calibrated models, which I think that's a pretty popular use of entropy regularization.
Yeah, cool. I mean, I know quite a few uses of entropy regularization, but it all comes down to yeah, exactly on what you use it. You can't use entropy regularization on anything. Typically, you use it only on things that are positive. You know, so parameters that you want to be only positive. That's already a big restriction. So it couldn't be just any. This W can't just live in RD. You'd have to want it to live in the positive orphan. And there must be a reason for that. You know, something your model is asking you to only have positive parameters. So this happens in things like, you know, optimal transport, where your transport matrix, the only parameter you're trying to solve is the cost of moving something from one location to another, and cost is always positive, so you can use entropy. Okay, maybe we move on. Okay, so now we're going to talk about solving the training problem. I call it part 2, but really it's part 2, 3, 4, 5, 6. Everything is going to be solving the training problem one way or another from now on. And after introducing all that data, all that notation, you know, I just hit you with all this notation. I'm now going to throw it all away temporarily. Okay, so strange as it may seem. And I'm going to abbreviate everything for now. In fact, I think for this entire, mostly I'll use the following abbreviation. So now I'm going to get the loss function over our model and only on the ith data point. So pick out just one pair of data points. I'm going to add on the regularizer, and I'm going to call this the fi function, fi of w. This is sort of like hiding all the notation that's not needed for now. So I refers to which data point we're looking at, and w are the parameters of our model. So this hides the fact that we've already chosen the hypothesis function, we've already chosen the regularizer, we've already chosen this lambda here. And for now, we're just going to try and solve the training problem and not care about those choices, not care about making those choices. Sometimes I will open up the structure again and show you the notation inside, because when we need it, when we need to exploit that it has this particular shape. But for my lectures, I think for this summer school, we're not going to pull this apart much. So one important structure remains. So let me show you. So on the left-hand side here, this is the training problem. But if I introduce my notation, well, first, I can move the regularizer into the summation. And the reason I can do this is because it's not a summation, it's an average. It's 1 over n here. So even putting it inside the average makes no difference. And now I can replace this loss plus regularizer by what I defined up here, fi. And with this simplification, my problem now becomes, I need to minimize the average of these functions fi. Now we'll call this the training problem now. So I want to minimize an average of fi's. And then when I drop the I notation, if I just write f, I mean it's the average of all of them. Okay. So mostly for my lecture, I have lectures today and tomorrow. I'll mostly talk about exploiting the structure of the fact that we have to solve a problem that is a finite sum. We have to minimize an average of fi's, and this n could be very, very large. And if just a few cases will I show you again the structure up here. Is that okay for now? This notation is important because we'll use it a lot.
Rob, can I ask a question?
Yes.
Don't you want the regularization to have less of an effect the more data? So wouldn't you want the regularizer term outside the sum?
So first, this is a very good point. The more data I have, I would like the regularizer to have less of an effect, which often would mean I should choose lambda maybe in a certain way. But the second point about having it in or out of the sum, it doesn't make a difference actually from the optimization point of view. They're actually just equal. Like, I mean, you can see even here the first line that I put the regularizer outside the sum, it's equal. It makes
Depending on the size of your data, so if you change the data, you need to find a new lambda.
Find a new what, sorry?
A new lambda.
A new lambda, yes, that's true. Yes, I change the size of the data. If I have more data, I should probably use a smaller lambda. And that's tricky. That's actually, there's not even like, I'd say, I don't know, a simple solution to that or what to do. That's a good point. Cross-validation is always the fallback for most people. Okay, anything else? Moving on. Okay, so we're going to get to our first algorithm, and I'm just going to present it without much of a song and dance. And what our main reference algorithm will be just gradient descent. I'm hoping that maybe everyone has seen sort of a motivation for why using gradient descent. If not, it's just that the gradients point in the downhill direction if you take a very small step. So let's look at the gradient of our problem. Well, the gradient of a finite sum of functions is the finite sum of the gradients. So both summations and gradients are linear operators. So you can just like change them around. And the gradient descent algorithm is going to look like this for me. You have to choose an initial set of parameters W0, and I'm just going to choose 0. Doesn't have to be that way. In fact, random choices are, I think, more popular in ML. Then you have to choose a step size, and we'll talk a lot about this in the coming slides, is alpha. It's a positive number. And then we're going to iterate. We're going to iterate over t. We're going to start at a WT, which will be initially W0, and we're going to take minus step in the direction of the gradient. So here's the full gradient, but times alpha, which is the step size. It should shrink a little bit, so you take cautious steps, and you make sure you're going downhill. This is going to be our first reference algorithm. The thing is that we want to talk about, I want to tell you when does gradient descent work and when it doesn't work, when can we guarantee it works and whatnot. And the truth is that optimization in general, without assumptions, is extremely hard. In fact, you can write down most all physics as an optimization problem through variational techniques, and you can write down any physics, pretty much any problem reality as an optimization problem. And that gives you a hint that it's too hard. So let me show you one particular optimization problem, which is the needle in the haystack type problem. So this is a 3D plot of a function that depends on x and y, and the height is the function value. So this is a function that's flat almost everywhere, except it has like a thin, sudden spike, makes it incredibly hard to find. So to solve this to find this minima, you pretty much just have to put a grid over the XY space and just search everywhere. So if you want to be able to solve solve optimization problems, you need assumptions, because without assumptions, you get these awful things. In fact, you can do worse than that. Here's another hard optimization surface. This is called the Echolder function. It's called the Echolder function because it's meant, you can like put loads of eggs all over the place. They just sit there standing. This is also awful to solve, really hard. Although I did come up with a method that actually solves this problem, just for fun. But in general, almost no optimization problem can search through all these millions of local minima to find the fact that it has just one global minima hiding that's a little bit deeper than all these other little holes.
Excuse me.
Yes.
Oh, I guess I was just wondering, so I guess in a lot of deep learning scenarios, the optimization, I guess the function you're optimizing over might not be very well defined. So I guess I'm just kind of wondering how, like, looking at like these example functions where you are able to actually like plot them out and look at the slope helps to like design ML or at least get an understanding for it when you have these very complex, maybe not as well defined cases.
So when you say not defined, do you mean like there's no functional form like this? Like there's no equation that describes the function, or? Can you hear me? I didn't understand what you meant by well defined.
I guess like if you have it's like, okay, I want to determine how many cats are in an image. So I have a bunch of cat images.
Okay.
And I want to like be able to optimize my algorithm to, I guess, give the best result over a bunch of them.
Well, I mean, the first thing you have to do is make it defined. I'd say that problem of determining how many cats are on an image, for now, is defined in human language. We kind of know what it means, but we need to give it mathematical meaning to be able to do anything. So at some point, you're going to have to write down a network, convolution, maybe a convolutional network, or maybe just a transformer, since it's all matters now. And then you're going to have to write a loss function, probably a cross-correlation loss function, and then you're going to try a little bit of regularization, and then eventually you're going to have this an awful equation that describes your function, but it's going to be written down in code and mathematics. At which point you can even visualize parts of the loss function. It doesn't look like this one, but it's highly non-convex as well.
Okay.
I don't know if I answered your question, to be honest. Though. Is that?
I mean, it was kind of a loose question, to be fair.
That's good. I'm happy with these questions, by the way. It feels like at least I'm interacting and talking to you all. So all questions, any loose questions are good as well. But yeah. Okay.
I would also have a question.
Yes.
So back when I did an optimization lecture, it was a few years ago, we actually had Rosenbrock functions all over the place.
Yes.
And I was wondering, are you still using these currently in research, or are they too simple as an example?
Yeah, this is great. Of course, I know the Rosenbrock function. Optimizers love it. I would say they're too simple to indicate. I can say a lot about this actually, because I'm from the optimizer culture. There was a phase in optimization where we collected lots of test problems, like huge numbers of test problems, hundreds of weird functions like the one you've seen here. And we used to run our new methods on all of them to see if it would do well. It's a bit of a crazy thing to do because it's not really relevant for practice, because most of these functions, even the Rosenbrock they all have particular pathologies, and they're designed by optimizers to be pathological. And because there's no such thing as a universal optimization algorithm, there's no free lunch in optimization either. There's a little point in you testing one optimization method on all these different toy functions like the Rosenbrock, this eggshell. Because what will it tell you? If you want to do well in all of them, you have to have a bad algorithm that's extremely slow and extremely cautious. So people still do it, but I wouldn't say machine learning is a big thing. No one really, I think, cares that much. But there will be one slide with the Rosenbrock function at the end of my talks, just to so you see it's pervasive.
Okay. Thanks for the insight. Mm-hmm.
Yeah. Okay. All right. So now I'll show you something where gradient descent can work. I got this logistic regression problem. So logistic regression means L2 regularizer, linear model, logistic loss. This is called the 4-class data set. I think it's just some artificial data set, or no, maybe it represented a simple game. It has 860 data points. It has only 2 features, so I can plot it. And what you're looking at here is the X feature and X1 and X2 features, 2 features. These concentric ellipses are the level sets of the function. So the way to see this is that it's actually a bowl, a deep bowl, And each one of these ellipses is where the function has equal height, if you've never seen a level set. The red point is the minimum. And the blue balls is actually gradient descent with a particular step size, 0.7. So it worked perfectly. You can see the blue balls just going in a apparently straight line to the solution. So it works sometimes. And can we prove that this works? And why did it work? So first, in my previous slides, I tried to emphasize a little bit that, if you just choose, you can't just choose any optimization function or any function and hope to minimize it. Some of them are horrific. They will necessarily be pretty much impossible to solve. But if we specialize with some assumptions, in this case, we're looking at what's a convex and smooth problem, and I'll define what that is. Then we can prove that gradient descent, stochastic gradient descent, and many other methods will work. So the first thing is convexity. Convexity.
Yeah, can you hear me without the microphone?
I can hear you good.
Yeah. Oh,
it's fine. You don't need to be close to the thing.
oh, okay. Well, I'll give it to you later. So what do you actually mean by work? Because even gradient descent, it will never actually get to the minimum, like the actual minimizer. You're only getting closer and closer. So I'm just wondering what you mean by work.
I mean, work is that it'll get as close as you want. You can define how close you'd like to be, and it will get there.
Okay, so you have like, in this case, you're assuming we have an infinite number of steps, and we just want to get as close.
No, infinite even. In fact, I won't show asymptotic things. I will show non-asymptotic. So given you want to be an epsilon distance, there's a finite number of steps that'll get you there.
Okay.
Yeah, it's a good question. Anything else? Okay. So now comes the
One more question, sorry.
Yes?
Do you have any sort of guarantees for the non-convex case like that?
Yes, we do. I mean, there are some guarantees. For the global minima, there are a few interesting classes of non-convex functions that people look into, that you can prove that this will happen even if it's non-convex. But to be honest, it's always very specialized non-convexity. It's always like functions that still have a unique global minima and almost no stationary points. Yeah, if you want global, like this kind of convergence, you want something that's going to work, converge as close as you like, finite number of steps, and non-convex, it's going to be non-convex in a way that there's only one stationary point anyway. There's only one place to go. But I can talk more about that. Actually, I did some work in non-convex, especially because of the interest of deep nets, which are non-convex.
Great, thanks.
I had a question. I was wondering, I think in practice, sometimes you don't even really want to converge to the global minimum because it would just overfit to the data. So does that idea come up when you're trying to find good optimizers, and do you take that into consideration?
Yes, this is a good question. This question is a little bit too good because I don't have a great answer. So early stopping is one thing that's often done in some problems where you stop the algorithm early. You don't want to go too far because you might start overfitting. Now, early stopping happens especially in inverse problems when you know that you're trying to fit something that's not the true problem. You're using an approximation and you can't overfit to noise. So say you know that your data is corrupted with noise and you can't converge all the way, because if you converge all the way, what you're going to do is you're going to fit the perfect noisy version of your data. But here, we're not going to assume that type of noise. I'm just going to assume the only noise we have is that we have a finite set of data, and there could be much more data we're missing. But that's a very particular kind of noise, so early stopping is not going to help here much. At least I can't quantify how much. And then in non-convex, it's hard to say because when you have non-convex, stopping early, you don't even know where the algorithm is going anyway. It's going to a stationary point. So I'm not sure. That's a good question. A little bit too good.
All right, thank you.
There was a pretty interesting paper that was called something like sharpness aware minimization. I don't know if you've heard of it. So like you talked about in the non-convex case where you have this ton of global minimizers, and which one should you try to aim for? And they argued that the sharpness of the minimum, like not only look at the value of the function there, but also look in a neighborhood, and the sharpness of that minima was related somehow to the robustness of where you're converging to.
Right, yes. So you should prefer big, deep, flat minimas as opposed to sharp little ones, because if it's sharp little one, it means that you change your parameters a little bit, your model suddenly completely changes. And this means that small perturbations to inputs can make your model change its behavior a lot. And it can be open to adversarial attacks and all kinds of things. So yeah. This is a part of the long discussion all around the non-convex world, which is an ongoing and difficult.
There's one more question.
Good point. Okay, I guess I'll move on. And now comes this, I think the talk, my lectures become, from here to the end, they gradually become more painful because I'm going to go over assumptions and techniques, technical things, little by more and more. So just a heads up. So first, the reason why convexity makes our life so much easier is that a nice property to have when solving problems is that if you knew that the gradient was 0 at a W star, then that W star is the smallest possible function value. So f of W star is smaller than f of W for every other W. That makes our lives very easy because the gradient then serves as a great signal if you're close or far from the solution. If the gradient is big, you're far. If the gradient is small, you're getting close. And this nice property is satisfied for convex functions. So a convex function, I'll talk more about convexity in a second, but let me give you one way of saying convexity is that at a point W, f of W is greater than the linearization of f around y. So that means it's f of y plus the gradient of y times the difference between y and W. And this is the local linearization, the tangent. So if this is true, you just need to choose for any, just choose y equals W star. And if the gradient is 0, you're going to have f of W star is 0, so this term is 0, and you're going to have necessarily that f of W is greater or equal than f of W star. So this nice property above holds for convex functions. Another way of saying it, all stationary points are global minima. Stationary point is a point where your function's gradient is 0. It doesn't move anymore. It's very locally flat. A little thing about, this is a little outdated, but a few words for convex machine learning. Deep learning, of course, is amazing, has major breakthroughs, but convex machine learning is actually used a lot. You'd be surprised. And this is now a bit outdated because this survey from Kaggle in 2017 across companies of what methods were they actually using. And I have been very cautious to label a few of them as convex optimization, but actually many more of these things are convex. But for sure, logistic regression, which is the second most used machine learning model across companies, is a completely convex machine learning problem. PCA and dimension reduction tools are often convex, but they can be non-convex. Support vector machines further down is definitely convex in most ways it's written. A few of these other things are also convex, but it depends exactly how they are using their decision trees or exactly how they set up their problem. So this is my way of saying that convex optimization is actually relevant. It's not just a theoretical construct or toy. It's still actually something that's used a lot. And that's it. Okay, so now I'm sure you're all incredibly motivated to learn about convex machine learning problems, given that previous slide. So here we go. I'm just going to define convexity in 3 different ways for you to make sure we're all on the same page. So the first definition is a function f that goes from Rn to R is convex if we have the f evaluated on any point interpolating between w and y. So here I have this parameter lambda that goes between 0 and 1. So as you change between 0 and 1, at 1, this interpolation equals w, at 0, it equals y. So it's basically all these blue points. Here's w. On the other extreme, here's y. 1 second. Hide this. Yeah. Here's y. And so this interpolation between w and y gives you all these function values here. So convexity is that f on any point interpolating between w and y is less or equal than the interpolation of the function values. So what that means is you get lambda times f of w, which is up here. And you get 1 minus lambda times f of y, which is over here. And this actually forms a line in lambda. If you think about it, this is a function of lambda, it's just a straight line. It's this dotted line here, which I've sort of mislabeled actually. This shouldn't be here, this should be down there. So this dotted line is the interpolation between f of w, always lies above f on the interpolation. So connecting two function values by their straight lines, they lie above the graph of the function. Another way, which I've already introduced very briefly, is that the function value f at w is always greater than the linearization of f around any y. So here's a depiction of it. Here's a point y. This dotted line is the linearization around y. And you can see that the dotted line lies entirely below the graph of f. So if I get any other point f of w and evaluate it here, it's above the dotted line. A final characterization, which is pretty hard to visualize, but I'll try anyway, is that the second order derivatives, if you take the gradient twice, you get a matrix, which is the Hessian matrix. And this Hessian matrix has positive eigenvalues. So what that means, one way to see this is that if you take any vector v that's the same size and shape as w, and you multiply on the left the Hessian and on the right, the resulting is a real number, and that real number is always positive. Another way to see this is that the Hessian, if you think about it, the Hessian is the rate of change of the gradient. So the kind of the eigenvalues of the Hessian, if they're positive, what they mean to say is that the gradients are increasing. One way to visualize this, and it's not easy to see, if you take one point w1 and a point that's greater, in terms of, it's just a real number, so W2 is greater than W1, then the gradient at W2 is greater than W1. So the inclination of the tangents is actually increasing. If you go from the negative orthant to the positive orthant. This is quite hard to visualize, I should say. And this interpretation, this idea of increasing only works in 1D. So the actual characterization is this here, that the Hessian is positive if you take any vector multiplying the left and right. Okay, so let's just go over some crazy convex, standard convex functions. One optimization trick that we often do, and it's kind of nasty, is that we work often in the extended reals. So I don't want to talk about what the domain of f is. Sometimes f is only defined on a ball or some other weird shape. But what many optimizers do is they ignore it. They say it's just defined on Rn, and they do it through a trick. Basically, if you find any point where x is not defined, we just say that f of x equals infinity. This strangely works. Even for convex functions, even if you do this, the result is still a convex function. For smooth functions, it's still a smooth function. For Lipschitz functions, it's still a Lipschitz function. Basically, many classes of functions don't care about you extending their domain and adding infinities where they're not defined. It's a very technical point. I'm never going to mention it again. But it'll sometimes happen. For instance, I'll write down logarithm, and I'm not going to be like, oh, x has to be positive. Nope, it can be infinity, in fact, where it's not defined. So examples of convex functions,
Sorry, if I can just have a.
Yes.
So this only works if the domain is compact, if the domain itself is convex, right?
Yes.
Okay, yeah. I just wanted to make sure that I understand. Okay.
Yes.
Thank you. Yeah, thank you.
A good point. If the domain is not convex, then the resulting function is something crazy that we can't really work with. So this is called the extended value extension of functions. But again, you don't need to worry about it. Okay, so the negative of log is a convex function. The logistic function where a and y are constants, or a is a constant vector, y is a real number. These are all convex functions. The hinge loss function is convex. And then there are many other matrix functions like negatives of log determinants, exponentiation, and exponentiation of matrices that I won't go over. Well, I actually have an exercise list, which I recommend you do sometime later tonight if you have time. Okay.
Can I ask a question?
Yes.
What do you mean by a domain being convex?
Yes, a convex set. So a convex set, one way to say it is anything that looks like a sort of blob. To be completely honest, it's just like a blob. It's either a blob or it's everything. And formally, mathematically, it just means if you get any 2 points and you connect them by a straight line, that straight line is inside the domain. So it's a characterization of sets as opposed to functions. Does that sort of answer your question? Yeah.
Yeah, thank you.
So convex functions, if you want to be precise, when we define convex functions, we have to have that their domain is also convex, a convex set, which means blob, that line segments between 2 points are contained. Okay, sometimes, in fact, many of my proofs I'll simplify even more, and I'll make a slightly stronger assumption than convexity, which is called strong convexity. So strong convexity, the nicest way to say it, I find, is that at any point W, your function f of W is greater than the linearization plus something extra that's positive. So it's even greater. And this positive thing is the difference between the 2 points, W, Y, in norm squared, and times a constant mu. And we say that this function is mu strongly convex if we have this constant here. So here's an example. I put the function which is the hinge loss, so the max between 0 and 1 minus W, just to be easy, plus the norm squared of W. And it's this blue line here. It comes down smooth and then pop, suddenly changes direction. It has a little kink. That's because of the hinge loss kicks in. And this function is strongly convex. And in fact, this entire thing on the right-hand side, oh, here we go. It highlights, it's nice. So here's the blue one. F of W is this thing. It's blue on the graph. Let's see if this works. Oh, yes, nice. The right-hand side, which is a lower bound, see, because it's less or equal, is this green line here. And it's a quadratic function because there's a squared term here. It's a linear plus squared means quadratic. And you can see that this quadratic function perfectly embraces the blue line, but it's always below. In fact, every time I talk about strong convexity, the honest version of strong convexity is this. If someone tells you that the overall training problem is strongly convex, that means that the loss is convex and the regularizer is L2 regularization. That's how you get strong convex functions in practice. So for instance, support vector machines with soft margins, which is a linear model over the hinge loss, which I haven't really explained why it looks like this, but that's the way it looks. Plus L2 regularization, that is a strongly convex function. There are many examples of non-strongly convex functions. Any neural network, dictionary learning, matrix completion, I could go on. The other assumption which we'll need throughout all of my slides is the fundamental assumption of gradient descent. And this is smoothness. We call it smoothness. So smoothness is where the difference between two gradients at x and y, their distance between them is upper bounded by a constant L times the distance between x and y. This is hugely important for gradient descent because it says that if two gradients are close, that means their inputs are close, x and y are close. So it gives you a sense of continuity in the gradient. So the gradients have, as they change slowly, your points are changing slowly. And I'll show you in one or two slides that this is a fundamental for gradient descent. Although gradient descent can work without it, but it helps a lot. So like convexity, there are many different ways, many different equivalent ways of writing down smoothness. And I'll just give you a few. So for instance, for a twice differentiable function, we have that f is smooth if the Hessian times any vector d on the left and the right is upper bounded by the same constant L times the norm squared of d. Another way of saying this is, in fact, the eigenvalues, in fact, this should be absolute value, to be honest, but the eigenvalues of f are bounded between L and minus L. My favorite way of using smoothness is this bottom one that says that it looks just like strong convexity, but the sign, the inequality is switched. So at any point x, your function at x is less or equal than the linearization around y plus the norm squared between x and x minus y and times the same constant L over 2. So this means that your function f of x is upper bounded by a quadratic. So in strong convexity, we had that lower bound, that quadratic lower bound. This thing is now an upper bound. It's always above the graph. So I had a small exercise. The exercise is I want you to show that regression is always smooth. So linear regression. So if I have a design matrix, capital X, so this capital X is a fixed matrix, someone gives it to you, and a vector B, and your parameters are W. Can you show that this norm squared of capital X transpose times Y minus B is a smooth function? And I've given a hint here, which you can use. And the hint is that there exists if you get the singular values of X, and I'll call sigma max the largest singular value of the matrix X. And the largest singular value of matrix X squared times D norm squared is greater or equal than X transpose D norm squared. So again, because I'm not actually there, I don't really know if I will, I won't. I'll just ask you guys to write this down and solve it. And tomorrow, if I'm there, or the day after, which hopefully one of these days I'll be there soon, someone has to tell me the solution. I just want to.
Excuse me.
Yes.
Oh, I guess this seems like a form of like Lipschitz continuity. Like, I guess we're looking at the Lipschitz continuity of the gradient. So I guess we're only from this. Are we only interested in like looking at the smoothness of the gradient and not anything like lower on? Like, I guess further derivatives.
Yes, great question. First, this is exactly Lipschitz continuity of the gradient operator. So that's good. For first order methods, when the gradient is the only real thing you're using, then you typically only need Lipschitz continuity of the gradient. For higher order methods that use Hessian derivatives, then you often need Lipschitz continuity of the Hessian instead.
Okay, that's interesting. Thanks.
Yeah. Okay, actually, this lecture is meant to be from 11 to 12:30, right? So we have like 8 minutes left.
Right.
Is that correct?
Yeah, so there's lunch after. How much, do you have an assessment for how long you would still need?
Oh, too long. I have infinite number of slides.
Okay. So because we had some interruptions, you can take some more time. There is lunch.
What time is lunch though for them?
So it's, I believe it's technically served at 1, but it should actually be ready at 12:30. The time should be 12:30, but
I'll just take 5 minutes extra then. That's it. I won't, won't go over. Lunch should be eaten hot.
well,
Okay.
I think it is scheduled for 1 for like different reasons, but they will probably already be there at 12:30. But that basically means that you can, you can probably take like 10 minutes extra. Or something like that.
Okay, I'll just take it as a few minutes extra. So visualizing smoothness is easy enough. Sorry, question? No. No?
Rob, you can keep going.
Keep going?
Yeah.
Okay, keep going. So one of the consequences, one of the equivalent ways of writing smoothness, I said, is that f at every x has an upper bound, which is quadratic. And what this looks like visually is that this big black smile is f of x. Then at every point y, you can draw this tangential quadratic upper bound, which makes this blue smile. And it's always above f. It's literally above the graph. Okay, so examples of smooth functions are, I wrote convex quadratics. I don't know why, because any quadratic is smooth. So you don't need to be convex. Just a quadratic is a smooth function. Logistic function is smooth. Trigonometric functions are smooth in this exact sense. And there are many more. Okay, but it wouldn't be fair if I didn't give you a counterexample. So a counterexample of a smooth function is this one. This is the L1 norm of the parameters W. So in 1D, the L1 norm is just a sharp V. And this is not a smooth function because there exists a single point at 0, which is this blue one here, which because of the sharp corner, it's impossible to stick a tangential quadratic upper bound. Notice how it crosses below the black lines. So this is a problem in one sense, to say it's smooth, but it's not a problem often in practice because when we have these kind of functions, non-smooth functions, they're often the regularizer, or if they're not the regularizer, we separate them out from the function and we treat them using what's called proximal steps, which is a different
Robert, there's
kind
a question.
Yes.
Oh yeah, about your last comment about convex quadratics, doesn't it depend on A whether it is convex or concave?
Exactly. Depends on the matrix A to be convex. A has to have positive eigenvalues. But
okay, so it's, yeah.
Yeah, but for any A, it's smooth. It doesn't matter. Because to be
okay.
smooth, you have to have bounded eigenvalues. So there has to be a lower and upper bound on your eigenvalues. And actually, for any fixed matrix A, there are lower upper bounds with eigenvalues. Just compute the largest, the smallest. They're finite. They have to, they have to stop somewhere.
Okay.
So all quadratics are smooth. But a good point. For convexity, not all quadratics are smooth. Depends. A has to be have positive eigenvalues. Good point. Okay, so now this is just my slide saying that not everything is smooth, and we actually have techniques for dealing with non-smooth things, and I'm not going to teach you those techniques because we don't have time. So just a fun caveat of things you will not learn. Okay, and the last thing I want to hammer in, it's very important, is that smoothness is super cool for gradient descent. Gradient descent loves smoothness, really loves it. This is where it shines. And the reason is quite simple, more or less simple. The reason is the following. Let's say you want to minimize f of w. You want to make f of w as small as possible. And you know that there is a quadratic upper bound on f of w. The nice thing about quadratics is that they're very easy to minimize if you have a quadratic. And because it's an upper bound, if we try to minimize the upper bound, it might push down f of w. So let's try and find the minimum of this right-hand side. And it's not just any quadratic, it's a beautifully convex quadratic, because the second order term is just identity matrix. That A matrix we had before, here it's identity. It's just identity times L. So let's find the minimum of the right-hand side. We're going to take the gradient of the quadratic term and the gradient in W, right? Because I want to minimize in W. So first we have f of y, that's dead, there's no W. Here, between the inner product, there's only a W here. And because inner product is a linear function, so I don't know if I define this, but inner product is just it's the gradient transposed times the other vector. Okay, it's like the @ symbol in Python, if that helps, which might not help. If you take the gradient here, all you're left with, if you take the gradient in W, all you're left with is the gradient in Y. And the final term, if you take the gradient of the normal squared, the 2 drops, cancels with the 2 down here, and you're left with L times W minus Y. And if you want to find the minima, you need to set the gradient of this quadratic to 0. So I'm going to set it to 0, equals 0. And now it's very easy to isolate W. Who can tell me what the isolating W looks like in this equation here? The equation here. It looks like this. You can pass the gradient to the other side, you pass y to the other side and divide everything by 1 over L, and you get W equals y minus 1 over L times gradient. Now this is very curious. If you think about what this means from the perspective of starting at y, if y was your current parameters, it's saying you should take a step in the negative direction of the gradient with a step size 1 over L. And this is fundamentally why smoothness is good for gradient descent, because a gradient descent step minimizes the quadratic upper bound of smoothness. And this is going to show, we're going to use this to prove that it converges beautifully. So I have a little exercise. You guys, everyone should write it down because I'll need to use this later. So I need this. So using this fact that I just showed you, that if we minimize the quadratic upper bound, this is the minimizer. W equals y minus 1 over L gradient at y. Can you show me that these following 2 inequalities hold? So what they are is that f evaluated at y after taking gradient step minus f of y is smaller than a negative number, and this negative number is minus 1 over 2L times the normal square of the gradient. And after you've proven this, you can show right away that the next thing holds, that if W star is the minimizer of f, then necessarily f of W minus f, f of W star minus f of W is less or equal than this negative gradient normal squared quantity. And that just happens by saying that f of W star is always less or equal than f of y minus, or f of anything, right? F of W star is less than f of anything. So to prove this, the solution is just this. I want you to get this W, this particular W, and I want you to plug it back into this inequality up here. So where we have f of W, I want to see f of y minus 1 over L times the gradient. And on the right-hand side, this y can stay, it's fine. But this W, I wanted it to be substituted out as well by y minus the gradient. And this W here as well, I want it substituted out. If you substitute this out by yourselves on paper, and trust me, you have to do this by yourself, otherwise you will not fixate, you will not really learn it, you will find this inequality here. And this inequality gives you shows you directly how much the function decreases if you take a gradient step. It's practically a proof of convergence in one step. There are some other steps, okay, but this has already gone a long way in one step. Okay, so I hope all of you will do that and you will internalize this lesson forever and forever after doing the exercise. Okay, and now what I will use my last 3 minutes is to very quickly show you one proof of convergence already for gradient descent, one of the easiest ones, and that is if your function f, which is the total training problem, is mu strongly convex and smooth, then we get the following linear type of convergence for gradient descent. So gradient descent, again, is from WT, you take a step in the negative direction of the gradient, but for simplicity, I've chosen a step size already, 1/L. No coincidence, just like I had in the previous slide. Then what we will show is that the distance between our iterate WT minus the optimum in norm squared is less or equal than a number, I'll talk about this number in a second, to the power t, so this is exponentiation to t, times the initial distance of W1 minus W star norm squared. Now this number here, I didn't emphasize this enough, I think, but mu is always a number smaller than L, because mu is a lower bound of the eigenvalues of the Hessian, L is an upper bound. I should have probably shown you that more carefully. And because mu over L is less than 1, 1 minus mu over L is also less than 1. So this is a number that's less than 1 that's being exponentiated. So think of it as being like a half. So there's a half to the power t. So it's really shrinking very quickly. Think about half to the power 100. What this means in terms of complexity, and I have an exercise actually on my webpage in the link in the first slide, which I'll go back to actually. What this means in terms of complexity is that if you want your distance of WT minus W star norm squared divided by your initial distance to be less than epsilon, so you can choose epsilon, then that means the number of steps you need to take in your algorithm has to be greater or equal than L over mu times the logarithm of 1/epsilon. So we call this an order log over epsilon type of convergence. Now, the important thing to focus is that logarithm is a function that grows very, very slowly. So epsilon here could be very small, and you would still get a very reasonable number of steps. On my webpage, you'll find an exercise sheet for complexity and rates, and it'll explain this kind of logic that goes from this number here to this complexity result down here. What this means in a plot is if you plot on the y-axis the distance to the minimum, so in other words, it's WT minus W star in norm squared. On the x-axis, you plot the number of iterations, and here we get the straight blue line. And that's because, sorry, I put the y-axis, the distance to minimum in logarithm scale, in log scale. And you can see it because if you take the logarithm of that previous result, I have that the log of the distance in iterates is less or equal than t times the log of this number. And it's linear in t. Okay, so examples of strongly convex and smooth functions include logistic regression plus L2 regularization, linear regression plus L2 regularization, a few other things, but not that much. And the proof, I think I'm going to have to go through the proof very quickly, and then that will be, then you'll be free to eat and take a break. So the proof looks like this. It's really very simple. You get the distance between WT plus 1 and W star in norm squared, and you simply substitute out what is WT plus 1. And WT plus 1 equals WT minus 1/L times the gradient. So then we substitute here. And then you expand the squares. So you multiply out WT minus W star times the gradient. So first we have WT minus W star squared. We have 2 times the inner product between these two components. And then we have the gradient squared. But it's also the L term, so the L becomes squared as well. The difficult thing we will tackle first is this inner product. We're going to reduce this to something like that we recognize. And fortunately, If you look at the definition of strong convexity, where I've chosen y to equal w star, so now I have w star, f of w star is greater than this quadratic, and you rearrange it, you will see that it gives you an upper bound of f of w inner product. So the gradient of at f with the inner product of w star minus w is now less or equal than this strange term. And this just comes from rearranging the definition of strong convexity. If I plug this in, this upper bound on the inner product, this term, this minus mu over half times the norm squared of the w minus w star goes here, becomes this minus mu over L, and this minus f of w minus f of w star, it's always evaluated w equals wt, becomes this term here. So this is as far as we got. So what's next? Next, we're going to handle this norm squared of the gradient. Now the norm squared of the gradient comes from that little exercise which I want everyone to do so they internalize forever, which is that f of w star minus f of w is less or equal to minus 1 over 2L normal gradient squared. This is called the descent lemma, by the way. Descent because it shows you are descending, that your function is getting smaller. If you just rearrange this, you pass the gradient to one side, you pass the function values to the other side, you multiply by 2L, you get this. So you get this beautiful upper bound that the norm of the gradient squared is less or equal than 2L times f of w minus f of w star. Plug that in, and we're going to get a little cancellation because here we had 1 over L squared. So if you times that by 2L, you're going to get 2 over L. Now, this 2 over L times the difference of the functions cancels out with this minus 2 over L difference of functions. And what we're left with is 1 minus mu over L times the norm squared of the iterates. Now, this is the end of the proof because what the rest of the proof just follows by induction. Like this is true from t plus 1 to t, and you can just keep unrolling this for recurrence. And every time you do, you're going to get another power here times this constant. So for those, it looks nice, looks easy, the proof. If you really want to learn it though, if you really want to know if you understand the steps and you could do it, you should do the proof again, but not for a step size 1 over L, for any alpha. And you should ask yourself, what does alpha have to be for this converge? And you'll see that it doesn't have to equal 1 over L. There's a whole range of values. And I want someone to come up and tell me one day, what is that range of values? Okay, I'll stop here. Next lecture, I'll have to talk about what happens to the convergence of gradient descent if we just drop strong convexity and we just have convexity plus smoothness, which is a much bigger family of functions, much, much bigger. You'll see the same method will converge, exact same method, but the rate, instead of being this exponentiation, it's just 1 over t, where t is the number of iterations. Okay, so that's it. I'm just going to leave the first slide any second now. Oh dear. Yes, so if you want some exercise sheets, I put 3 exercises on convexity, smoothness, complexity, and ridge regression. And you should do all these 3. They're here on my webpage, gowerrobert.github. Okay, that's it. Thanks, I can see the clapping. That's good enough, that's good.
Thanks, Rob.
Okay.
Right, I believe lunch is on the other floor, 17th floor.
I'll see everyone tomorrow, either online or in person, depending on my COVID test.
Sorry,
so for those of you that have not yet picked up your dad, we do have some slides out. Also, everybody should pick up at least one open text. There's 2 tests. the badges on the field. So please make sure you at least take one badge with you to the Alabama or anyone housing. That's taken 3 days. It'll say that on your return state and on the badge. There's always additional tests available at security, but I also have a on the fifth floor of CPA as well. So as you're moving through the program, feel free to pop in and let us know if you need extra tests. The security can also give you extra if you take your badge and make sure you're doing that like on a regular basis. If for some reason you do test positive, let us know because we have to be contact based. Everyone will be in contact with you. Quarantine.
What is the HR orientation?
The HR orientation is just on Zoom. I believe it's 1:30, and it's only 15 minutes long, so it should be pretty quick. You can always pull it up on Zoom here as well, if that would be easier to do that. Or you can just log on your computer. But I think since so many people are in one space, it would probably be better just to sit on the screen or have one person share their computer.
Yeah, so come back at 1:30 here to do it.